Hello everyone, it's me, Billy Younger again. I'm here to work on a problem regarding linear expansion. So let's get started by me sharing my iPad screen with you. Okay, so here's the problem. It says a temperature controller involves a bimetallic strip constructed of aluminum and copper and connected at their ends by rivets. Each of the metals is 1.6 millimeters thick and at 20.0 degrees Celsius, the strip is 10 centimeters long and straight. Find the radius of the curve made by the strip when it reaches 115.0 degrees Celsius and the angle subtended by that curved strip. So let's get a little drawing first to get an idea of what we're actually solving here, and then we'll work on the solution. I don't know why this is, oh, there it is. So let's start with solution. So I looked up the coefficients of linear expansion for both aluminum and copper, and what I found was the coefficient of linear expansion for aluminum was in fact 25 times 10 to the negative 6 reciprocal Celsius degrees, and the coefficient of linear expansion for copper turns out to be 17 times 10 to the negative 6 reciprocal Celsius degrees. So we did need that information. Our bimetallic strip initially will look something like this. And if, let's assume this side right here is the aluminum, and this side is the copper, and what we know is this is 10.0 centimeters at 20 degrees Celsius. Okay. Now, what we plan on doing is, in fact, increasing it to 115 degrees Celsius, at which time the aluminum will get quite a bit longer while the copper will not get quite as long. I'm going to draw something obviously not to scale, but try to give you an idea of roughly what it looks like. So we're going on the assumption that it will basically bend like this, and that this bend is actually a part of a circular curve. Now, it doesn't necessarily have to be exactly like a part of a circular curve, but we're using that as a model, if you will. And we are asked for this angle theta, that's the second part, but we're also asked for this radius right here, which I'm going to say goes roughly to the center of the copper side, and therefore the radius of the outer part, since that's the longer part, of course, that will be a little bit larger, and we're going to make the assumption that that distance is r plus delta t, where the delta t is in fact the thickness of the metal strips. And according to the problem, the thickness delta t was 1.6 millimeters, which is also 0.16 centimeters. We did have the L0 equal to 10 centimeters. We have T, the initial temperature, being 20.0 degrees Celsius. And we have the final temperature being 115. Ooh, I didn't leave myself very much room for that one, but being 115 degrees Celsius, like that. So, how are we going to do this? Well, we know from our introduction to radians, for instance, which you probably experienced in a trig portion of your pre-calculus class, or if you ever took trig before that. But normally what they tell you is that the part of an arc length, S, is given by the radius of the circle, the part of the circle, times theta, the angle that subtends the arc. So this basically applies to something whose arc length which notice it's curved, is S. The angle it subtends is theta, and the radius is r. So that's what we're going to apply. Now, the one thing we do know is that even from the drawing, you can tell that the theta, the angle that it subtends, is the same for both of them. So I can say the angle theta is in fact S over R. So I'll say it's going to be S, the arc length, if you will, of the copper, and then divide that by the radius that I labeled R. And that's going to have to be equal to the arc length of the aluminum divided by its radius of curvature, which we're assuming would be R plus delta T. So in principle, we can just solve all this by hand, and I could even leave the symbols in there. But what we are going to make use of course, is the fact that the L, the final length, is equal to the initial length times 1 plus alpha delta capital T. And remember that delta T is a change in temperature. So that also came from the original form that you might be more used to, which is delta L is equal to alpha L0 delta T. But we're choosing to use this version. So the case for the copper becomes L0 for the copper times 1 plus alpha for the copper delta T, which is going to be the same for both of them. That all is going to be divided by R. And then we have L0 for the aluminum times 1 plus alpha aluminum. And again, the same delta T, so I don't need to subscript that. But what I do need to do is put the radius as R plus delta T. And that's specifically because, as you can tell from the drawing, the edge or the radius that we're talking about solving for is to the center of the copper thing, which would be the copper side, which would be roughly here. And then the center of the aluminum side would be right down the middle here, and therefore the separation between them should be the actual thickness of the plate. So if I draw it right here, you can say this is delta T, and so is this one. So both of those thicknesses are individually delta T. Now, what I can know is since the L0 is the same for both of them, I can actually go ahead and cancel them out from this equation. That's not, since it's multiplying, we can do that. And we can go ahead and cross multiply. By the way, this is really the only time you use that terminology of cross multiplying is when you have two ratios equal to each other. So in the left-hand side, we've got a numerator and a denominator. In the right-hand side, we've got a numerator and a denominator. You multiply the numerator on the left by the denominator on the right, and set that equal to the product of the denominator on the left and the numerator on the right. So that's what we're going to do now. I'll keep the symbols in as long as I can, and then we'll plug the numbers in. So what I'm going to get is 1 plus, oops, didn't switch back to my purple writing. So what I'm going to get is 1 plus alpha copper delta T times R plus delta T, notice two different delta T's there, is equal to R times 1 plus alpha aluminum delta T. Now we're going to distribute all of that, and what we'll get is R plus delta T plus alpha copper delta T times R plus alpha copper times delta T times delta lowercase t. That takes care of the four terms. Let's see. Yes, I have the R It's a two binomials. So there's a r plus delta t that has two terms. There's a 1 plus alpha cu delta t that has two terms. So we multiply them, we should actually get four terms, and you can see we actually have three equal signs here, so it's clearly four terms. So that's a nice little check. Now we're going to do the other side, and I'll go ahead and distribute that. So that's r plus alpha aluminum delta t times r in that case as well. And actually, I didn't really leave myself enough room, so I'm going to try to zoom in there and put this plus a little further this way, and then I'll put the r right there as well. So basically what we can see is automatically I can subtract r from both sides, and that gets rid of that leading r. But we can also take the two r terms and leave them on the right hand side, and that's what I'm going to do right now. And I'm going to put the non r terms on the left hand side. So on the left hand side, what we get is delta t times 1 plus alpha copper delta t, and that takes into account this term, that's the alpha delta t term, and it also takes care of this term, which is just the delta t term. Now I'm also, as I said, subtracting or pulling the r term to the right hand side. So ultimately on the right hand side have a common factor of r, and that common factor of r will be alpha for aluminum. Technically, it'll be times delta T, but I have a common factor of delta T as well, so I'm going to pull that out in front too. So I'll say that's just alpha aluminum. But then on the other side, when I bring the alpha copper delta T R in here, then that's going to become a minus, and it'll be alpha copper. And then finally, I got the delta T, and now I can see that I've taken into account this term, which led to obviously this part, and this term, which led to obviously this part. So with all that, I should be able to solve this analytically with for just the r, and the r should be equal to 1 plus alpha copper delta t over alpha aluminum minus alpha copper. And of course, that all is going to be multiplied by delta t in the bottom. So we're going to have a delta lowercase t on the top and a delta temperature T capital on the bottom. So that should be our whole answer. We can plug in the numbers now. This will be 1 plus the coefficient of linear expansion of copper is the 17. No, it is, yeah, the 17 times 10 to the negative 6 reciprocal Celsius degrees times the change in temperature, which is 115 minus 20.0 degrees Celsius. And then over here, I get 25 times 10 to the negative 6 reciprocal Celsius degrees minus 17 times 10 to the negative 6 reciprocal Celsius degrees. And then, of course, we also have to multiply that by delta T, which would be 0.16 centimeters over, and of course, the math from 115 minus 20 is 95.0. And that, of course, would be Celsius degrees, or degrees Celsius, which technically I've been calling it Celsius degrees when you do a subtraction. So that comes out that way. Now we can go ahead and say 17 times 10 to the negative 6. Oops, my calculator, I jumped the gun and my calculator wasn't on yet. So 17 times 10 to the negative 6 times 95.0, and that should give me 2 sig figs, which is 0.001615. And then I have to add a 1 to it, and that'll be the whole numerator of the left-hand fraction. So we get 1.006, or excuse me, 1.001615. And that actually should have the units, that should have no units because it's specifically Celsius degrees times Celsius degrees reciprocal, and that gives you no units, and then you added a 1 that had no units. Additionally, on the bottom, what we're going to do is take 25 times 10 to the negative 6 minus 17 times 10 to the negative 6, and that's going to give me 8 times 10 to the 1, 2, 3, 4, 5, 6. That gives me 8.0 times 10 to the negative 6 Celsius degrees reciprocal, which means that unit is going to come to the top and it'll be Celsius degrees, which we can also call degrees Celsius. Now I've got to do the little fraction to the right. I should also take a second to mention that when I multiply the 17 times 10 to the negative 6 reciprocal Celsius degrees times the 95.0 Celsius degrees, that gave me a unitless number, but that unitless number was really only allowed to have 2 sig figs, which meant the 1 and the 6, after the 0.00, the 1 and the 6 were the only two that were significant. So I'll underline the 1 and the 5. Then I added it to 1, and of course 1 has any number of decimal places, so that doesn't alter it. It's still the same 1 and 6, but now that we've got a 1 on there, we actually have bumped up to, in fact, have 5 sig figs. Because remember, addition and subtraction don't really use significant figures like multiplication and division does. It actually uses a number of decimal places. Similarly, when I subtracted 25 times 10 to the negative 6 minus 17 times 10 to the negative 6, that actually gave me 8 times 10 to the negative 6. But technically speaking, that 8 is in the last digit of 10 to the negative 6. So the 8.0, the 0 is actually non-significant. Now I'm going to take that 0.16 and divide it by 95. And in that case, I'm going to get 0.001684. And that unit should be centimeters per Celsius degree. And of course, that Celsius degree is going to cancel out with the Celsius degree that I said was going to pop to the top from the 8.0. In this case, we also had 2 sig figs divided by 3 sig figs. So we really only have 2 sig figs, which means the 8 and the 4 are not significant figures. So now we can go ahead and multiply these numbers. I'm going to take the 0.001684. I'm going to multiply that by 1.001615. Notice I am carrying those non-significant digits. When I do that, I get 0.001687. And really, that's only supposed to have 2 sig figs because only the 1 and 6 were sig figs. So the 8 and 7 is not going to be sig figs. And then, of course, I've got to divide this by the 8.0. So I'm going to take my answer, and I'm going to divide by 8 times 10 to the negative 6. And that gives me, in fact, well, this was just 8.0 times 10 to the negative 6. And there's no units in the bottom. After I do that, that actual division problem, I get 210.9. It's actually 8663, but I get 210.9 roughly. And that's our answer. Only technically we only have 1 sig fig, so I would still report it as 211 centimeters. So now that I've actually solved for the full length, of course, we could convert that 2 meters and it'd be 2.1 meters. Again, we had to use one extra figure that wasn't a significant figure to see the difference, or to see part of the difference anyways. In principle, this would just have to be called 2 meters with no decimal places, 2 point, just 2 point with no decimal places. But now that we've done that, we can also use this information, the new result, for instance, to find out what the actual angle will be. So the angle that it subtends is the angle theta. So what we can write is theta is equal to the length of the actual copper side, say, divided by the radius, which we just found. So we can actually do that. Of course, we never actually fully calculated exactly what the length was. We just did all the parts except for the calculation. So in order to do that, I'm going to have to write the 10.0 centimeters that it had as the initial length. I'm using this formula, L0, 1 plus alpha. Excuse me. Let's fix that a little better. L0 times 1 plus alpha delta t, that being the final length. That's for the formula I'm using. So this 10 centimeters is the L0, then plus 1, and now I'm using the copper, and the copper is the one with the 17 times 10 to the negative 6 reciprocal Celsius degrees. That has to be multiplied by the 95.0 Celsius degrees. And then, of course, we can close off that with a square bracket, and then we divide all that by the 210.9 centimeters. Again, showing that the 1, the 0, and the 9 are not sig figs. And this should come out technically in radians. So I can then convert that to meters as well. So first off, I'm going to go ahead and calculate what that new length is. In other words, the numerator. So, and then we'll also have that number as well. But anyways, what we do is 10.0 times parenthesis 1 plus 17 times 10 to the negative 6 times 95, and that's the entire part. So we get 10.1, or excuse me, 10.0162 centimeters over 210.9 centimeters. So I'm going to divide this by 210.9, and that gives me 0.4, oh, excuse me, 0.04, 0.0475 radians. And of course, 1 radian, or excuse me, of course, pi radians is 180 degrees. So I can take this radian number and divide it by pi. So I divide it by 3.14159, plenty of digits. And now I'm going to multiply that by 180 times 180, and that gives me 2.72 degrees. That's how long it's supposed to be. Of course, remember, we only had one sig fig, so only the 4 was significant there, and therefore we only have one sig fig in this one, so the only the leading 2 is significant there, so we'd have to call that like 3 degrees. But either way, we now have the answer. It subtends that, and of course, we also now figured out the final length of the bimetallic strip. It's 10.01, or basically 1 centimeter longer, roughly 1 or 2 centimeters longer than it was at 20 degrees Celsius. So I hope that makes this problem a little less scary, and I hope it is something you can use in the future as a trick to, do little things like calling the longer radius r plus delta t. That's it. Have a good day. Bye-bye.